I'm Christian Deppe. I'm a researcher at the Technical University of Munich at the Institute of Communication Engineering. I will present you our work on non-adaptive and adaptive two-sided search with fast objects. It's a joint work with Alexej Lebedev. In traditional search theory, the goal is to find a hidden object in a given search space in minimum time. And the object is stationary and hidden and not moving. And this model is called one-sided search. What is now two-sided search? Two-sided search was introduced by Bernhard Koopman. He was member of the Warfare Operation Research Group of the US Navy during the Second World War. And in their model, the search object, is allowed to move after each test. And their proposal was to provide an efficient way to search for enemy submarines. And they call this search two-sided search. They consider a probabilistic model. In 2010, the late Rudolf Alexej proposed a combinatorial model of two-sided search. And he asked, how many questions do we need? What is the minimum number of questions? What was the model he proposed? He proposed the following model. We have a graph G with n vertices and e edges. It's an undirected graph. So the search space are the vertices from 1 to n. And the object to be found occupies one vertex of n. And these vertexes, of course, are known to the searcher. And at any time, and for any test called a test set, the searcher can learn whether the target is located at some node T or not. And after each test, that's now the special thing, the target can move k times to any vertex adjacent to its current location, or it can stay at the same place. So it can move in the graph. So it can go from neighbor to neighbor, and after each test, it can move k times at most. And the search finished when the searcher is able to locate the object with some predefined accuracy S. Of course, it's not possible to give the exact position, because after each test, the object is allowed to move. So we are satisfied if we can give S positions and know that one of these positions is the one with the object. And now the problem is we want to find the location of the target, of course, with a certain accuracy, in minimum time in the worst case. So we do worst case analysis. That means somehow we have an object with reject in a way that it's for the searcher, it's really the worst case. We need some notations. So by small dj, we denote the location of the target at time j. So we have such a vector if we have a search of length n. So n is the number of tests from d1 to dn. And of course, there's a path from di to di plus 1 of length at most k because of the rules. And we have a function f, which gives us the test result of the test t. So it gives us the 0 if the searched object is not in the test, and if it gives us a 1 if the searched object is in the test. And the sequence T1, T2, and Tn is called an adaptive strategy if the j's test depends on the previous j-1 test. That means if we do a test here, the test tj, then we know the result of the previous test and can take the results into our account and do the next test. That is an adaptive test. By big DI, we denote the set of possible positions of the target after the i's test. That means we start with I equals 0, so we start with all elements. So we start with d0 is equal n. Then we call an adaptive strategy for a given graph G as successful if for any possible sequence of movements we have for some di that it is smaller equals than s, if I is lesser equal than n. That's the reason we do an adaptive strategy. Because if we know that some di is smaller equal s, then we can stop there and give the positions and we can finish. So S star of G is the minimum S star such that there exists a G S star successful strategy. And such a strategy is called an optimal GS strategy. How is our work related to other works? So for example, it's related to group testing. So in group testing, you always have more defective. Now we have only one defective. But the difficult thing is now this defective can move. Also, there's a relation to graph searching. There exists this popular game of a cop and a robber. There are also some similarities in this game. What is known in our model I described here? So for k equal 1, adaptive optimal strategies are known for cycles, for paths, and for complete regular trees. And I want to present you our new results. We give you an adaptive optimal strategy for cycles, if k is greater than 1, and also an adaptive optimal strategies for passes, if k is greater than 1. Furthermore, I will give you a non-adaptive optimal strategy for passes of accuracy as equal 4k. And I will show you that a better accuracy is not possible. Let's start with cycles. For cycles, we got the following result. By NC and S, we denote the maximum n such that there exists an CNS successful strategy of length n. And you see then this n grows exponentially in small n, the number of tests. And somehow this is not really surprising because the idea of the direct proof is somehow that you do a splitting strategy. That means you split your the number of you split your objects into two halves and ask for one half. After this, you get a new number of possible positions and you split them again. So it's like binary, generalized binary splitting algorithm. And we can show that this splitting algorithm is optimal, and we can have so many numbers of positions. That's the maximal number of positions n is given. Furthermore, we showed that an accuracy smaller than 4k is not possible. What is the result for paths? For paths, for NP-NS, we denote again the maximum n such that there exists an PN successful adaptive strategy. And you see here already that the result looks very similar. So for S greater equal 4k, again, we have this generalized splitting algorithm, and we can show that this is optimal. But what is different here, we only can show that there do not exist a successful strategy with accuracy smaller than 3k. So there's a gap in it. There's a gap for S between 3k and 4k. And what happens for S between 3k and 4k? Let's look at the case when k is equal 1. Then, of course, if S is between 3k and 4k, it's 4. So only possibility. So we look at the path here, and we have the searched object, and it moves to the left, or it can move to the right, or it can stay, and so on. Now, what is an optimal strategy? The first test is like in a splitting algorithm. We ask for half of the elements here. Then we get a yes or no. Let's assume we get a yes. So these are the possible positions. So the element can move once. So we have to add this position. But now Optimal is not to split again. What we do now is we ask for these two elements here. Now, if the answer is yes, then we can stop, because then the element can move here or it can move here, and we have accuracy 4, and we can stop. But if the answer is no, then we reduce the elements here by 1. And again, we do the same interval tests and so on until we reach this situation. We are left with 5 elements, and we ask these interval questions. Now if you get a yes, then we have these 4 positions. If you get a no, then we have this 4 positions. So in each case, we finish with the correct accuracy. And we get the following theorem. This kind of interval tests are optimal. Also, if k is greater than 1. And we get this result here. That n of n 3k plus l, where l is between 1 and k, is equal to 2nl plus 4k. You see now it grows linearly. It's different, but we can solve it and get a better accuracy. Now we ask the question, is it possible to find a non-adaptive strategy? What is a non-adaptive strategy? Because it's different, you cannot ask the question in parallel. That doesn't make sense. Because we want to allow the object to move always between the questions. So that means you want to give the question beforehand, and then you ask them in a row. And after each question, the object can move. So in this case, non-adaptive strategy just means the questions do not depend on the previous test result. And this is also the advantage. We do not take care of the previous test result. And the disadvantage is, of course, if we locate the element before the end of the strategy, we have to keep track of it, because we cannot stop, because we don't know the answers. And so we cannot stop like we did in the adaptive case. So we have to keep track on it. So the question is, how much more tests do we need? And my colleague Alex came then with an example for k equal 1 and s equal 4. And he showed me a strategy that's the following, where we need 6 questions, like in the adaptive case, for 16 positions. And it's exactly this strategy. What is the idea? That's the reason why I present you the adaptive strategy for k equal 1. If you look now here, you see somehow the first question here is also a splitting question. And then if you look here, we get, let's assume we get here no, then you see here somehow again this interval question. And also to the other side, if you look, first you have this interval question, then you have the complement question. You have here 2 zeros and here all 1s, here again 2 1s, and so on. So it's somehow, it's like in the very similar to the adaptive case that you have this interval questions here inside. Furthermore, you can check if you get a yes in between, then you keep track of the element, because you see here, you have here's this ones and here's this ones. And again, so it cannot escape. It always stays here. And at the end, you know where it is. Not exactly, but with accuracy 4. So this strategy works. And it's as good as an adaptive strategy. That's somehow surprising. And we can generalize. So first, let's do it for k equal 1. For k equal 1, we get the same number we need the same number of questions like in the adaptive case. And furthermore, if n is bigger than 6k, then we cannot have a better accuracy. So then somehow it's really optimal. And also, if k is greater equal 1 and s is equal 4k and n is big enough, then we always find a non-adaptive strategy with the same number of questions like in the optimal adaptive case. So we can really generalize this idea. What are the conclusions? We consider optical combinatorial non-adaptive and adaptive two-sided search. And we described optimal search strategy for parsers, graphs, and cycles. And an interesting open question is the characterization of strategies of minimal length for trees. And it's also interesting to find the following. Consider the problem for other popular networks like grids and cubes. We did this, but for every grid, you need somehow a new idea. Somehow one have to find really classes of grids and classes somehow where you need the same idea. It's not so easy. And furthermore, of course, we want to generalize our model with errors. That means you have some test results which are incorrect. And so it's related to a coding problem. Okay, thank you for listening and thank you to our sponsors.